There are places in space where galaxies disappear. Empty spheres millions of light years across that shouldn't exist. Today, we explore the cosmic void. Hit the subscription button if you want more mysteries like this. Now, we begin this journey. In 1981, astronomer Robert Kirshner and his colleagues at the Harvard-Smithsonian Center for Astrophysics were conducting what they believed would be a routine galaxy survey. Using spectroscopy to measure the redshift of galaxies in the constellation Boötes, they expected to map the standard cosmic distribution, galaxies scattered across space like cities across a continent. What they found instead was silence. As they plotted galaxy positions in three-dimensional space, a pattern emerged that made no sense. Where their telescopes pointed toward Boötes, they found almost nothing. Not darkness caused by obscuring dust, not a simple, empty patch, but a spherical region of space nearly devoid of galaxies, stretching across an incomprehensible volume. They called it the Great Void in Boötes, later simplified to the Boötes Void, and it represented the first time humanity had discovered something not by finding it, but by finding its absence. The numbers were staggering. In a region approximately 330 million light-years in diameter, they detected only 60 galaxies. Mathematical models predicted there should be 2,000. The void contained less than 3% of the expected galactic population. To understand the scale, if you could travel at light speed from one edge of this void to the other, civilizations would rise and fall, stars would be born and die, and 330 million years would pass before you reached the other side. But here's where it gets strange. The only Boötes void isn't just large, it's spherical. Cosmic structures form through gravitational collapse, which tends to create filaments, walls, and irregular shapes. Perfect spheres are extraordinarily rare at cosmic scales, yet the void maintains remarkable spherical symmetry across its entire volume. Cosmologists ran the numbers. If galaxies formed randomly according to standard models, the probability of finding such a vast, empty, spherical region by chance is less than 1 in 10 million. The void's existence suggested either spectacular statistical luck or something fundamentally wrong with our understanding of cosmic structure formation. Dr. Greg Aldering of Lawrence Berkeley National Laboratory later confirmed what Kirshner's team suspected. The void is not a statistical fluke. It's a real structure, or rather, a real absence of structure that demands explanation. The discovery triggered immediate questions. How did such a region form? Why is it spherical? Most troubling of all, are there others? To understand why the Boötes void challenged physics, you need to understand how the universe organizes itself. Following the Big Bang, matter distributed itself nearly uniformly across space. Nearly, but not perfectly. Tiny quantum fluctuations created regions with slightly more or less density. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, growing into galaxies and galaxy clusters. Less dense regions became voids as their matter drained away toward gravitational attractors. This process creates what astronomers call the cosmic web, a vast network of galaxy filaments, walls, and clusters surrounding enormous voids. Think of it like soap bubbles. Galaxies cluster on the surfaces where bubbles meet, while the interiors remain relatively empty. By the 1990s, extensive surveys confirmed this structure throughout the observable universe. Voids are common, typically ranging from 30 to 150 million light-years across, containing perhaps 10 to 20% fewer galaxies than average. The Boötes Void is different. It's more than twice as large as typical voids and nearly completely empty. It doesn't fit the bubble pattern. It's an anomaly within an anomaly. As mapping technology improved through the 1990s and 2000s, astronomers discovered that the Boötes Void wasn't alone. The Capricornus supervoid, discovered in 2015, spans 1 billion light-years. The cold spot supervoid stretches across similar scales. The Eridanus supervoid, the sculptor void, each presenting similar puzzles, regions of space far emptier than cosmic evolution models predict. But the Boötes Void remains special. Its proximity to Earth, only 700 million light-years away, means we can study it in unprecedented detail. And the more we study it, the stranger it becomes. In 2004, astronomers discovered something remarkable. The few galaxies that do exist within the void aren't randomly distributed. They cluster along the void's edges, as if avoiding the interior. Some concentrate in a narrow filament threading through the void's center, a cosmic highway through emptiness. This pattern suggests the void didn't form randomly. Something shaped it. Something organized it. Something we don't yet understand. But the evidence forces us to confront an uncomfortable possibility. What if the void represents not an absence of matter, but the presence of something else entirely? In 2007, Dr. Lawrence Rudnick at the University of Minnesota made a discovery that deepened the void mystery considerably. Using data from the Wilkinson Microwave Anisotropy Probe, WMAP, which maps the cosmic microwave background radiation, the afterglow of the Big Bang, Rudnick found something unprecedented. When he looked toward the region of the Boötes Void, he detected a cold spot in the microwave background, approximately 10 microkelvin colder than surrounding regions. This shouldn't be possible. The cosmic microwave background shows the universe as it was 380,000 years after the Big Bang. The Boötes Void is a structure that formed billions of years later. These two phenomena exist at completely different epochs in cosmic history. They shouldn't correlate, unless the void is influencing light itself. Rudnick proposed the integrated Sachs-Wolfe effect. Photons from the cosmic microwave background lose energy as they pass through expanding voids, arriving at our telescopes slightly cooler than expected. The correlation suggests the Boötes Void has been growing, expanding, pushing galaxies outward for billions of years, longer and more aggressively than standard void models predict. The void isn't just empty, it's actively emptying itself. Scientists discovered something even stranger when they measured the void's expansion rate. Standard cosmic expansion, driven by dark energy, causes all of space to stretch over time. Voids expand faster than average because they contain less matter to resist expansion. The Boötes Void, however, expands approximately 20% faster than theoretical models predict. Dr. Irene van de Weygart from the University of Groningen studied this phenomenon extensively. His team's 2016 analysis revealed that the void appears to contain a higher concentration of dark energy than the surrounding universe, as if some unknown process is concentrating this mysterious force within the void's boundaries. Dark energy constitutes approximately 68% of the universe's total energy density. It drives cosmic acceleration, pushing space itself apart. But we've never detected variations in dark energy concentration across different regions. It should be uniform, like a field. The Boötes Void suggests otherwise. If dark energy can concentrate in certain regions, our entire understanding of this fundamental force requires revision. Think about what this means. The void isn't just empty space expanding. It's a region where the fundamental properties of space-time itself differ from the rest of the universe. But this represents just one piece of a much larger puzzle. In 2013, the Baryon Oscillation Spectroscopic Survey, BOSS, mapped the Boötes Void in unprecedented detail. Their analysis revealed a troubling discrepancy. When astronomers calculate the total mass within the void based on galaxy counts and gas observations, they measure approximately 2% of the expected value. But when they calculate the mass based on gravitational effects, how light bends around the void's edges, how neighboring structures move, the answer is different, significantly different. The gravitational measurements suggest the void contains approximately 15 to 20% of the expected mass. That's still far below normal, but it's 10 times more mass than we can actually see. Where is this missing mass? The obvious answer is dark matter, invisible matter that interacts only through gravity. Dark matter outweighs visible matter 5 to 1 in the universe, so finding invisible mass isn't surprising. But here's the problem. Dark matter should follow galaxies. If galaxies were expelled from the void, their dark matter halos should have been expelled too. Yet, something with mass remains, something that bends space-time, something we cannot see, cannot detect, but cannot deny exists. Dr. Yan Chuan Kai from the University of Edinburgh studied this phenomenon extensively. The void contains gravitational signatures inconsistent with simple emptiness. We're detecting curvature in spacetime that demands explanation beyond standard void formation. The void is hiding something. The most remarkable discovery involves the motion of the void itself. In 2018, astronomers measured the peculiar velocity of the Boötes Void, its movement through space independent of cosmic expansion. They expected minimal motion. Voids generally drift slowly due to their low mass. Instead, they found the void moving at approximately 600 kilometers per second toward the constellation Centaurus. For comparison, our Milky Way galaxy moves at about 600 kilometers per second toward the Great Attractor, pulled by the gravitational influence of trillions of solar masses. What could push or pull a void? By definition, voids contain almost no matter. They have virtually no gravitational influence. They should be the most stationary structures in the universe. cosmic anchors, barely drifting. The velocity suggests something massive, something with gravitational influence far exceeding visible matter, is affecting the void. Either something inside the void is pushing it, or something outside is pulling it. Dr. Planck collaboration studied cosmic flows across vast scales and concluded the Boötes Void participates in bulk flows inconsistent with its visible mass content. We observe dynamics requiring mass we cannot detect. Analysis of the 60 galaxies that do exist within the void revealed another anomaly. These galaxies aren't primitive or young, as you might expect in an underdeveloped region. Many are elliptical galaxies, old, evolved systems that typically form in dense galactic clusters through millions of years of gravitational interactions and galaxy mergers. How did old, evolved galaxies end up isolated in the void? Dr. Michael Plinus from the National Observatory of Athens studied this phenomenon. The galaxies within the Boötes Void show characteristics of galactic populations formed in dense environments, then somehow transported to isolation. It's as if they were abandoned there. More puzzling still, these galaxies show peculiar motion patterns. Instead of moving randomly, they exhibit subtle, coordinated movements as if responding to gravitational influences we cannot identify. In 2019, detailed surveys revealed that many void galaxies are actually aligned along a narrow filament threading through the void's center. This filament measures approximately 200 million light-years long, but only 10 to 20 million light-years wide, a cosmic thread through emptiness. The filament contains more galaxies than the rest of the void combined, yet still represents only a fraction of expected galactic populations. It's as if something drew galaxies along a specific path, abandoning the rest of the void to emptiness. Perhaps the strangest evidence comes from determining when the void formed. Standard models suggest voids form gradually over billions of years as matter drains toward gravitational attractors. The Boötes Void, given its size and emptiness, should have required at least 8 to 10 billion years to reach its current state. But spectroscopic analysis of void galaxies tells a different story. The galaxies show evidence of rapid evacuation. Their stellar populations indicate they formed in normal environments, then suddenly found themselves isolated approximately 6 to 7 billion years ago. Not gradual drainage over eons, but relatively rapid expulsion on cosmic timescales. Dr. Rien van de Wijgaard's team analyzed this temporal signature. The void appears to have formed faster than gravitational drainage alone can explain. We observe evidence of accelerated evacuation, as if something actively repelled matter from the region. What mechanism could evacuate hundreds of galaxies from a region hundreds of millions of light-years across in just 1 to 2 billion years? The evidence extends beyond simple gravitational evolution into the realm of forces and processes we don't yet understand. The void formed too fast, expanded too aggressively, and exhibits properties too anomalous to fit comfortable explanations. Something happened in that region of space. something that left a scar 330 million light-years across.
So, how do physicists explain the Boötes Void? Several competing theories attempt to account for its extraordinary properties. The primordial origin hypothesis suggests the void originated from quantum fluctuations in the early universe. According to this model, regions of slightly lower density after the Big Bang never accumulated enough matter to form galaxies efficiently. Over billions of years, what began as a mild underdensity grew into a massive void. Dr. Jean Innestat, who pioneered void studies, supported this view. The largest voids likely trace back to the largest quantum fluctuations in the earliest moments of cosmic time. They are fossil signatures of the universe's birth. But this model struggles to explain the void's spherical symmetry, its rapid formation, and its dynamic properties. The gravitational drainage model proposes that massive galaxy clusters surrounding the void simply pulled matter outward, evacuating the interior through gravitational attraction. The Boötes Void sits adjacent to the Boötes supercluster, which contains thousands of galaxies and immense mass. Dr. Volker Springel's supercomputer simulations of cosmic structure formation can produce void-like regions through gravitational drainage alone. However, even his most aggressive models require billions of years longer than observations suggest the Boötes Void needed to form. The dark energy fluctuation theory offers a more radical explanation. If dark energy isn't perfectly uniform, but varies slightly across space, regions with higher dark energy density would expand faster, pushing matter outward more aggressively than surrounding regions. This could explain the void's rapid formation and unusual expansion rate, but it requires accepting that dark energy, which we barely understand, varies across space in ways we've never detected anywhere else in the universe. This forces us to reconsider fundamental assumptions about cosmic structure. Some physicists propose even more exotic explanations. Dr. Laura Mersini-Houghton at the University of North Carolina suggests the void might represent evidence of the multiverse. In her model, our universe exists alongside countless others. Before cosmic inflation separated them, these universes could have left gravitational imprints on each other, cosmic bruises where universes brushed against each other. These imprints would appear as anomalously large voids where matter was gravitationally influenced by structures in adjacent universes. The Boötes Void, in this framework, is a shadow of something that exists in a parallel cosmos. It's speculation built on speculation, but it's speculation grounded in serious physics. Dr. Subir Sarkar at Oxford University proposes something equally radical. What if we're not looking at a void, but at a region where our understanding of gravity breaks down? At the extreme scales the void represents, hundreds of millions of light-years, perhaps Einstein's general relativity requires modification. Modified gravity theories, like modified Newtonian dynamics or F of R gravity, might explain why the void behaves so strangely.
Perhaps at these scales, gravity doesn't work quite the way Einstein predicted. Testing these ideas requires observations at the very limits of our technological capabilities. Recent breakthroughs suggest we're on the verge of understanding voids far better than ever before. The Dark Energy Spectroscopic Instrument, DESI, which began full operations in 2021, is mapping the universe in unprecedented detail. Over 5 years, DESI will measure spectra from 35 million galaxies and quasars, creating the most detailed three-dimensional map of cosmic structure ever achieved. Early DESI results have already refined our understanding of the Boötes Void's boundaries and internal structure. Dr. Julian Guy, a DESI collaboration member, notes, "We're discovering that what we call the void is actually a complex structure with subtle features we missed in earlier surveys. There are hints of subvoids, density gradients, and organization we couldn't resolve before." The Vera Cruz Rubin Observatory, expected to begin full operations in 2025, will survey the entire visible sky every few nights for 10 years. This will allow astronomers to track void evolution in real time, watching how galaxies move, how voids expand, how structures evolve. For the first time, we'll observe voids not as static structures, but as dynamic entities changing before our eyes. The James Webb Space Telescope, launched in 2021, offers another tool. Its infrared sensitivity allows it to detect faint, distant galaxies we've never seen before. Applied to void regions, JWST might discover hidden galaxy populations, dwarf galaxies, dark galaxies, or exotic structures too faint for previous telescopes. What if the voids aren't as empty as we think? But perhaps the most promising avenue involves gravitational waves. When massive objects accelerate, colliding black holes, merging neutron stars, exploding supernovae, they create ripples in space-time itself. The Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo detectors have revolutionized astronomy by detecting these waves. Future gravitational wave observatories, including the space-based LISA mission planned for the 2030s, will be sensitive enough to detect phenomena across cosmic scales. And here's where it gets interesting. Dark matter, if it exists in unusual configurations, should produce gravitational wave signatures. If the Boötes Void contains exotic dark matter structures, collapsed dark matter regions, dark matter voids, or configurations we haven't imagined, gravitational wave detectors might finally reveal them. Dr. Alessandra Buonanno at the Max Planck Institute for Gravitational Physics explains, gravitational waves provide a completely independent way to probe cosmic structure. They reveal mass distribution regardless of whether that mass emits light. For voids and their mysterious mass discrepancies, this could prove transformative. The void raises an uncomfortable philosophical question. In 2003, philosopher Nick Bostrom published his simulation hypothesis. If sufficiently advanced civilizations can create detailed computer simulations of universes, and if they run many such simulations, then statistically, we're more likely to exist in a simulation than in base reality. Cosmic voids like Boötes present an intriguing connection to this idea. Computer simulations require computational shortcuts. You don't simulate empty space with the same detail as interesting regions. Voids could be unrendered regions, cosmic spaces the simulation doesn't bother detailing because nothing's there. The void's properties, its spherical symmetry, rapid formation, statistical improbability, might be artifacts of simulation boundaries or computational optimization. This is wild speculation, far beyond current scientific testability, but physicists like Dr. Silas Bean at the University of Washington have proposed actual tests for simulation hypothesis. They suggest looking for regular patterns in cosmic structure that might represent underlying computational grids. Voids, with their peculiar geometries and dynamics, might provide clues. It's a thought experiment that challenges our assumptions about reality itself, and it emerges directly from studying the universe's strangest emptiness. The most profound implications emerge when we consider what empty space actually means. Quantum physics reveals that vacuum isn't empty. Even in perfect vacuum, quantum fields fluctuate. Virtual particle pairs spontaneously appear and annihilate. The Casimir effect demonstrates that nothing exerts measurable forces. Space itself seethes with energy. The Boötes Void, despite its name, isn't empty. It contains hydrogen gas, cosmic rays, neutrinos, dark matter, dark energy, and the quantum vacuum itself. What makes it a void isn't absolute emptiness, but the absence of galaxies, organized matter. This distinction matters. The void challenges us to understand not why a region is empty, but why matter failed to organize there. Why didn't gravity do its job? What prevented galaxies from forming? What expelled the galaxies that did form? Dr. Carlos Frank, director of the Institute for Computational Cosmology at Durham University, frames it this way. Voids are laboratories for understanding cosmic forces. In dense regions, many effects overlap: gravity, pressure, magnetic fields, radiation. In voids, we isolate fundamental processes. They reveal physics we can't see anywhere else. Zooming out reveals something remarkable. The Boötes Void isn't isolated. It's one bubble in a cosmic foam extending across the entire observable universe. The cosmic web, that vast network of galaxy filaments and walls surrounding voids, represents the largest organized structure in existence. This web spans 93 billion light-years, the diameter of the observable universe. It contains approximately 2 trillion galaxies, organized into hundreds of billions of voids, filaments, and clusters. It represents the universe's fundamental architecture. What shapes this architecture? Dark matter provides the gravitational scaffolding. Dark energy drives the expansion, but the specific patterns, why certain voids form where they do, why the web exhibits particular symmetries, why structures organize on specific scales, these questions touch fundamental physics we don't understand. The Boötes Void, as anomalous as it is, provides crucial data. By studying outliers, we understand the rules that govern everything else. Recent simulations by the illustrious TNG project, the most detailed cosmic simulations ever run, reproduce void structures remarkably well, but they struggle with the largest, emptiest voids. The Boötes Void lies at the edge of what simulations can explain. This suggests we're missing something. Some force, some process, some physical principle not included in our models. Consider the void across cosmic time. When light left the Boötes Void 700 million years ago, the universe was significantly younger. Galaxies were more actively forming. The cosmic expansion was slower. The void we observe represents a snapshot of the universe from that earlier epoch. By now, in the void's present, which we can never directly observe, it has expanded further. The few galaxies it contains have evolved, changed, perhaps merged. The void itself is larger, emptier, more isolated. In another billion years, the accelerating cosmic expansion will have pushed the void's boundaries outward. Galaxies on its edges will recede beyond observation. The void will grow darker, emptier, more isolated. In the far future, as the universe ages toward heat death, voids will dominate. Galaxy clusters will become isolated islands in an ever-expanding ocean of emptiness. Eventually, in trillions of years, accelerating expansion will isolate every galaxy, every star, every structure. The universe will become one vast void. The Boötes Void offers a preview of this cosmic future. It shows us what awaits: a cold, dark, empty universe where structures break apart and isolation becomes absolute. But this future remains trillions of years away. For now, the void presents mysteries more immediate and profound. What if other voids harbor exotic physics we haven't detected? What if they contain dark matter structures organized in ways we can't imagine? What if they're not voids at all, but regions where matter exists in forms we cannot yet perceive? These questions drive contemporary research. Every new observation of the Boötes Void refines our understanding while opening new mysteries. We began this journey confronting a sphere of darkness 330 million light-years across, an absence so profound it challenged our understanding of cosmic structure. We've traveled through evidence that this void is no simple emptiness. It formed too quickly. It expands too aggressively. It influences the cosmic microwave background. It contains invisible mass. It moves through space with purpose. It exhibits properties that demand explanations beyond our standard models. We've explored theories ranging from conventional physics to exotic speculation, primordial quantum fluctuations, gravitational drainage, dark energy fluctuations, multiverse imprints, modified gravity. Each explanation captures pieces of truth while leaving questions unanswered. The current scientific consensus acknowledges both what we know and what we don't. Yes, voids form naturally through cosmic structure evolution. Yes, the Boötes Void represents an extreme but probably natural example. But no, we don't fully understand its properties. No, we can't explain all its anomalies. No, we're not done learning. Recent observations continue revealing new mysteries. DESI data suggest substructure within the void more complex than expected. Gravitational lensing studies hint at invisible mass concentrations. Peculiar galaxy velocities suggest unknown influences. The void is teaching us. Every observation refines our understanding of how the universe organizes itself across the vastest scales. Every anomaly points toward missing physics. Every mystery drives technology forward. But perhaps the Boötes Void's greatest lesson isn't about voids at all. It's about the nature of discovery. We found the void by noticing absence. We probe it by measuring emptiness. We learn from it by studying what isn't there. In a universe filled with spectacular phenomena, exploding stars, colliding galaxies, massive black holes, the empty spaces teach us something equally profound. They remind us that understanding requires knowing not just where matter is, but where it isn't. Not just what exists, but what doesn't. The void challenges our assumptions, tests our theories, and reveals gaps in our knowledge. It forces us to confront uncomfortable truths about how little we understand the universe we inhabit. And that's exactly what science requires. Comfortable knowledge advances slowly. Anomalies drive revolution. The Boötes Void is our anomaly, our reminder that the universe remains far stranger than our theories suggest. Our invitation to keep searching, keep questioning, keep exploring. The universe is vast. The mysteries are endless. The journey continues. And somewhere in the constellation Boötes, 700 million light-years from Earth, a sphere of near-perfect darkness waits, silent, enigmatic, challenging us to understand. The void is patient. Are we ready to listen?